Hey everyone, and welcome. Today, we're going to tackle a programming problem that looks super simple on the surface. But trust me, it hides a really powerful secret about how to solve tricky challenges by focusing on what actually matters. Let's dive in.
All right, no messing around, let's just jump right in. Take a look at this list of numbers. If you were to multiply every single one of them together, what would you get? Would the final answer be a positive number, a negative number, or would it be zero? Just take a second to think about it. We'll circle back to this, but first, let's get the official rules down.
So here's the official goal. We need to build a function. Let's call it signFunc. Now, this function is kind of special. It doesn't care about the actual value of a number, like 5 or negative 100. It only cares about its sign. So if you give it a positive number, it gives you back a 1. A negative number, you get negative 1. And if it's 0, you get 0. Our job is to apply this function to the product of all the numbers in a given list.
Okay, let's make this real with a few examples. Look at this first row. You multiply all those numbers together, you get 144. That's a positive number, right? So signFunc spits out a 1. Now the second one, see that 0 in there? That's a spoiler. The whole product instantly becomes 0, so the function returns 0. And for the last one, we've got 3 negative numbers, an odd number, so the final product is negative and we get negative 1. The goal is pretty straightforward.
All right, so you see the problem, you see the examples. What's the first thing that pops into your head? What's the most obvious, direct way to solve this without overthinking it?
Yeah, you'd probably go for what we call the brute force path. And the logic is, well, it's dead simple. You just loop through the array, multiplying each number by the next until you have one big final product. Then you just look at that one number and ask, is it greater than 0, less than 0, or equal to 0? Boom, done. Easy peasy, right?
Well, not so fast. What if that array had thousands of numbers, and they were all pretty big themselves? That final product could become just astronomically massive. So big, in fact, that it might cause something called an integer overflow, meaning it's literally too large for the computer's memory to handle. And when that happens, our simple brute force method completely falls apart. There's got to be a better way.
And here it is. This is the big aha moment. The crucial insight is realizing we were never asked for the final product's value. We don't care if the answer is 144 or 1,044. We were only ever asked for its sign. That massive number is just noise. The only thing that matters is whether it's positive, negative, or 0.
And once you have that insight, it opens up a much smarter, much more elegant way to solve this. Instead of keeping track of some gigantic number that could explode at any moment, we can just track the sign as we go.
And this smarter path is all based on 3 super simple rules of multiplication, stuff we all learned back in grade school. I call them the 0 rule, the negative parity rule, and the positive rule. Let's break them down real quick. First up, the most powerful rule of all, the spoiler. It's simple. If you see a 0 anywhere in that list, it's game over. You can just stop right there, because anything multiplied by 0 is 0. The final product has to be 0. It's like an instant knockout punch.
Okay, next up is what I call the parity rule. And this is all about the negative numbers. Think about it. A negative times a negative gives you a positive, right? But then, if you multiply by another negative, it flips back to negative. Add a fourth, and it's positive again. So it all comes down to how many there are. If you have an even count of negative numbers, the final sign will be positive. If you have an odd count, it's going to be negative. And finally, the easiest rule of them all, the neutral rule. This one's about positive numbers. And here's the thing, they don't do anything. Multiplying by a positive number never, ever changes the sign of what you already have. So for what we're trying to do, just track the sign. Positive numbers are totally neutral. We can pretty much ignore them.
So, we've got our 3 rules, the 0 spoiler, the negative parity, and the positive neutral. Now let's see how this logic turns into a really clean, really efficient piece of code that won't ever blow up on us.
The first thing we do is set up a little variable to track our sign. We can call it ans, short for answer, and we'll start it off at 1. We're basically assuming the product is positive until we find evidence to the contrary.
Okay, now we loop through our numbers. And the very first thing we check for every single time is that spoiler rule. It's a number we're looking at as 0. If it is, stop everything, we're done. Just return 0 because we know for a fact the final answer will be 0.
All right, so it's not a 0. What's next? We check for the neutral rule. Is the number positive? If it is, we effectively do nothing. In the code, you'll see we multiply our ands variable by 1, which doesn't change it at all. And that's exactly the point.
Positive numbers don't affect the final sign. And finally, if the number isn't 0 and it isn't positive, well, it has to be negative. And this is where that parity rule comes to life in our code. We take our sign tracker, ands, and we multiply it by -1. So if ands was 1, it flips to -1. If it was already -1, it flips right back to 1. This one simple operation perfectly keeps track of the sign as we go. So to recap that elegant method real quick, you start with a positive sign. You look at each number one by one. If you see a 0, you're done. The answer is 0. If you see a negative, you just flip your sign tracker. If you see a positive, you do nothing. Whatever your sign tracker is at the very end is your final answer. No massive calculations needed.
This little problem gives us a powerful takeaway that goes way beyond just coding. It's a lesson in how to approach complex problems in general.
And this brings us to the core lesson. Effective problem solving isn't about raw computing power. It's about the power of abstraction, of stepping back to identify the fundamental principle and ignoring the rest. In this case, we realized the massive final product was just noise. Only the count of negative numbers in the presence of 0 actually mattered. And that leaves us with a final thought. In your own work, in your own projects, what are the big unnecessary calculations you're running? Where can you find the simpler underlying rule and focus only on what truly moves the needle? Something to think about. Thanks for watching.